First keynote speaker is Vikas Chandra from Facebook. He is the director of AI at Facebook Reality Lab, and he will give his keynote on efficient audiovisual understanding on AR devices. Please go ahead, Vikas.
Yeah, thanks, Wei. Thanks for the introduction. Good morning. And I just heard that there are attendees from 99 countries. So good afternoon and good evening as well to those of you who are in different parts of the world. It's my pleasure to be here. I've been working in the area of TinyML for a while now, not only at Facebook, but even in my last job before here when I was at ARM. TinyML has seen an explosive growth in the last few years, and I'm really, really excited about its future, where it can take us, because the future of ML is tiny. Now, in this talk, I'm going to specifically talk about the challenges and opportunities in the area of video understanding for augmented reality. But before I do that, let's talk about augmented reality. What exactly is AR? So what if we could augment the world that we see around us? What exactly will this look like when we get there? What could we do with the technology? Now, let's take a look at the glasses I'm wearing. This is not an AR glass, but assume it is. Now, in the current setting, I'm able to see things better. They improve the acuity of my vision every waking moment. But what if there were AR glasses that enhance perception in other ways as well? Now, every few decades or so, we reach an inflection point in how we interact with our devices. Let's take an example of laptops or desktops, right, where we use keyboard and mice to interact with the devices. Then came smartphones, where we basically touch and pinch and zoom and so on. And now we believe that at some point in future, there's going to be an inflection point where the interaction with our personal devices is going to be very, very different. It's been predicted that instead of carrying smartphones everywhere, we'll be wearing stylish glasses. These glasses will offer VR, AR, and everything in between. And we'll wear them all day and use them in almost every aspect of our lives. The distinction between AR and VR will vanish. The real and virtual worlds will just mix and match throughout the day according to our needs. So let's take some example of where it can help us do interesting things. So imagine if you're walking from somewhere late at night and it's dark outside. What if you could, with just a gesture, make it brighter? Other one is if you're going on a trip somewhere, but your loved ones are not able to come with you. And this has been especially true in the last 1 year with the pandemic. But what if you could spend some time with the people that you want to spend time with virtually anywhere in the world? And what if you can actually see better for people whose vision is not great, for people like me? So all of these are possibility, but it doesn't have to stop there. What if AR can also help with memory and cognition? Imagine if you're in a business meeting where you can see the results that you want to talk about right in front of your eyes. Or if you're traveling, where you can basically have the translation right in front of your eyes. And the last one, which I really like, is basically the ability for you to recall somebody's name if you have met them before. And this, I believe, is one of the key features that I think AR can enable. But we don't want the technology to be dumb. We don't want it to just pop everyone's name all the time in front of your eyes, because that's not really how human brains work, right? What we really want is to be context aware. We just want to things to pop up when we need it. Is the same way with our own. That's the same way our own memory works, and it will take always on, contextually aware AI to make that happen. You can think of AR as a tiny assistant with a perfect memory and an internet connection sitting on your shoulder, answering your questions and feeding you useful information all the time. That's our vision of what AR will look like. Now, let's take an example, a very simple example that we discussed with, putting a name to a face. What does it take to get there? So to begin with, we need a high resolution display that's bright enough to be visible in the daylight. It needs contextual awareness to figure out who is the person of interest. It can also be based on eye tracking, where it figures out who you're looking at to understand where the annotation needs to go. Image recognition will need to happen to associate an individual with an image. You need graphics to render the image. And there's a whole lot of technology that will happen or that needs to happen. You need world locking to attach the annotation to the person. Because if the person moves or if you move, you want the annotation to move with them. You need depth sensing, because if they move around and things get occluded or they go behind another person, you want the annotation to go behind with them as well. So what I'm trying to say is that even for a simple use case, a whole lot of technologies have to come together. Many of them exist, many of them do not exist. Many of them exist in a different form factor, and they may have lots of compute and power requirement that becomes challenging in a form factor devices like augmented reality glasses. So to deliver the best user experience, we have to deeply understand user context, and that is an interesting research area. Let's take a look at what would be a typical characteristic of an AR glass, right? It has to be socially acceptable. So it has to look like, sort of the glasses that I'm wearing. It has to be lightweight because you're wearing all day. It has to sustain all day usage. So you don't want to be charging your glasses multiple times a day. And because it's sitting next to your face, you have to be very cognizant of how hot does it get, because our phones do get hot occasionally if you use them quite often. So it is thermally constrained. And these are all the technologies that I talked about in the last slide. We need to figure out the optics and display, audio for things like superhuman hearing, computer vision, and so on and so forth. But one thing is very clear for those of you who do work in this area, that AI is going to play a really critical role for all of them. Now that we have made it clear that AI plays a critical role, the question is, why on-device AI? Why do we need to run these models locally on the glasses itself? And there are a few reasons. The first and foremost is privacy. So because these glasses are going to be there all the time, looking at the world the way we look at, we need to make sure that the data that they have stays on the device with the users and not shared with a computer that's outside of your home. The second was latency. So we do want the devices to react very quickly. Imagine a situation where your child is laughing or playing with their favorite doll or whatever, and in that case, you want the devices to react very quickly in capturing that moment. So every millisecond of latency matters. The third one is connectivity. So in the Western world, we do assume that we have internet connection everywhere, but that's not true in many parts of the world. Also, if you're going to go on a hike somewhere in a park where internet may not be there, you still want the devices to work. And the last bit is energy. So this is interesting because a lot of time people don't realize that it does take a lot of energy to also transfer data, sometimes orders of magnitude more. Wireless is not cheap. So in that case, it may make sense for us to do computation on device instead of sending data on the cloud. So these are all the reasons why we're really investing in making sure that whatever computational needs these glasses have, we can do them on device. But AR applications are not homogeneous, right? They come in all shapes and sizes. And here is an example or a laundry list of applications that basically show different characteristics, right? So let's take an example of speech or language or text to speech or language understanding. Arbitrarily, I have put together these four axes that identify what the characteristics are. So they are memory bandwidth, latency, usage frequency, and computational intensity. Right. So as I go through different use cases, for example, video understanding, eye tracking, hand tracking, keyword spotting, what I'm trying to highlight is that different applications look very different. They're not the same, both in terms of requirement of compute, memory bandwidth, latency, and so on. And that makes it very interesting research problem in how do we enable these use cases which look so different on a piece of hardware. What does it take to get there? So there are different challenges in making that happen. From the application side, we need to support heterogeneous applications, as I just described in the last slide. There should not be any user perceivable latency, and that's key because of the kind of use cases that we really want to see from these glasses. And it has to support high resolution data because there will be cameras capturing data at high frame rate, high resolution. We need to process them really quickly and efficiently. Now, from the system side, there needs to be a lot more efficiency that we need to have from these devices that doesn't exist right now. So we need to get like at least an order or two of improvement from where we are right now. The system also has limited compute and storage resources that we need to figure out how to get around. And also there are limited and shared bandwidth to system memory. And that's more of a hardware concern, and I'll talk about that as well, how we alleviate that. So as the title of the talk was audio-visual understanding, that's one particular use case that we are looking at is video understanding. Trying to understand the user activity and environment, what's happening around you. Let's take an example in the picture that's shown here. If your dog is playing with a ball and you basically say that, hey, take a picture of my dog playing with ball, you want the system to understand that it's your dog and not a dog, right? So it has to be personalized, proactive, and it has to be context aware. What if you don't have to tell it to take the picture and it understands that something interesting is happening and I should capture that? What does it take? What does it take to get there? The first one is data, right? You can have really sophisticated AI models, but if it's not trained well on real life and realistic data, then it will fail. So how do we train these models with limited label data that we have? And there are multiple approaches. I'll talk about them. Data augmentation is one, self-supervised learning another one. The second one is multimodal AI. So instead of having just one mode of trigger, for example, camera, which could be expensive, what if you have cascaded inference? So you can have cheaper modality to trigger the inputs. It could be audio, it could be something else like IMU. And once that triggers, you can have expensive modality to capture what you need to capture. And similarly, once multiple things trigger, then you can combine the inputs from all of those sources to get a higher accuracy of understanding. And the last one is more from system perspective. How do we get more power efficiency where these models will run? And again, we look at efficient compilation of multi-stream models. So if you have multiple modality, as I talked about in the second bullet, how do we run them together at the same time? Because the hardware may look different. An audio stream versus a video stream have different compute requirements. And then we also look at hardware-aware model design. And I'll talk about co-design a little bit more later in the talk. So what exactly is video understanding? There are two ways to define it. One is at a course level, we can understand what's happening in the environment, right? So on the left side, you can see getting a haircut or playing guitar or playing basketball or surfing. I mean, these are very high level, course level, description of what's happening around you. But you can also localize action. This person is sitting down or looking at a book or walking or doing something else, and you can have multiple localized action in a given video frame, and those are both interesting because depending on the needs, you can react very differently once you understand what else is happening in the scene. So I talked about the challenges of data. So one of the models that we use in video understanding is slow fast model. And you can train the model with data that you have, but a common technique is to augment the data by making changes to your data set. Now for image-based augmentation, one of the technique is called grid mask, where you put You take out essentially parts of your images, like as shown in the second figure, and you train the model with those augmented data set. And the rationale is that the model regularizes better if it doesn't see certain part, and for different images you'll do different sort of grid mask. Now we can do that here as well, but we have more information because it's video. Because it's video, we do understand what the subject is, and we can basically do sort of a saliency detection, which could be motion based. So in this case, for example, your video can understand that the subject of your video is chicken. And because the chicken moves more than the background, when you do grid mask, you can leave the subject as is and you can put the grid mask around it. And what that does is basically it makes the model even more smarter by learning the characteristic of the chicken more than the background. And this is one approach that we have used, and we have seen a good result in terms of what the accuracy of the model looked like with this approach. The second approach is to alleviate the data issue is self-supervised training. So even with we do a lot of data augmentation, we are still limited by labeled data. Now in the real world, we have really huge amount of unlabeled data. So how do we tap into that? So SSL, or self-supervised learning, is a common technique that's used, and there are different ways to use it. So the whole idea of self-supervised training is that you provide a data set without label, and you expect the model to understand the key idea in the data that you provide. So it needs to understand the semantic and extract information through that. So one example is contrastive loss. So if you provide similar representation for the same object through different views, and if you keep providing it and you tell it that they are similar, it will try to understand that what makes them similar. And the same thing for different representation of different objects. Other approach is spatial tasks. So if you have a lot of video frames, you can break the frames into tiles and you can rearrange them. And then the task is for the model to rearrange it back into how it was. And in doing that, it can learn a lot of information, latent information about the data. The third one is temporal, where you do the same thing but in time, where you can jumble up the frames in time and expect the model to put it back in the right order. So these are all the techniques where you can make the model much richer, even when you have limited data, labeled data. As shown in the table here, I mean, the definitely does help. As you can see, the accuracy of video classification with all of these techniques put together went up significantly high. Now let's talk about deployment challenge. So we have the data, we have trained the model, and we are happy with it. How do we run them? A typical cost of running a camera runs into hundreds of milliwatts. It's not cheap, and especially on a battery-constrained devices like AR glasses, these things can become a huge overhead. It also has transmission costs. So every time you take a picture, it's high resolution. You have to transfer to an SoC that can understand or run these models. Also, on the inference cost side, the video models are expensive. It can typically take hundreds of gigaflops to understand the user environment and action. So how do we get around that? So one approach is what is defined as a cascaded approach. So what if we use a cheaper modality as trigger, say audio or IMU? And when something interesting happens, then we can figure out what's happening around you from the vision perspective. Just as an example, an audio capture is orders of magnitude cheaper. So we can go from hundreds of gigaflops to tens of megaflops. It's a huge improvement. And also the transmission cost is cheaper because we could typically have these models run very close to sensors as well. So there are different approaches in doing that. And let's talk about one. So assume that you are traveling or you're you're walking around the city and your microphone is receiving inputs on the things around you. And you can detect transitions in your environment or action that's happening around you. And these typically are cheaper sort of inputs in tens of kilobytes. The models are not that big. It could be in tens of megaflops. And this model detects something interesting is happening. And when it detects that, it can enable or it can trigger the camera to come on. And this model is typically bigger. The inputs are also larger. Let's say you go into hundreds of megaflops, and it detects that there's potentially a basketball that's happening. Now, once that happens, then you can essentially start to go into full action where you start taking multiple frames on the camera. And you also combine that with the audio input. So this is where you actually have multimodal AI, multimodal input to your AI model. And this model could be huge, right? Because now your inputs are in tens of megabytes because you have multiple frames coming in. You also have the models which are much, much larger. It could be in tens of gigaflops, and you can have a lot more fine-grained action, right? So now you can detect whether it's somebody is dribbling or dunking or blocking, and then the system can react and do whatever is necessary to for this particular scene. So this is an example I just want to show where you can take advantage of multiple modality of input in a cascaded way, and this could be one approach to solve the problem of battery drain if the camera is on all the time. So this is an example from this work which happened at Facebook on slow fast network, and as you can see, to predict what's happening, you can have multiple modes of inputs. So you could have an audio signal with a very high sampling rate. You could have video with high frame rate. You could have low frame rate video as well. And then it starts to become interesting problems of how do you combine them? How do you do a deep fusion to learn better features from this sort of model? Okay, so we talked about deployment. We talked about the model. Let's talk about where hardware can play a role. So very a cartoonish picture of how an SoC looks like is shown here in this slide, where you have application memory, system memory. You have different IP, and let's say if you have a monolithic in an accelerator that's sitting on the system bus, and that's one way to do it. A better way to do that is folding the accelerators inside the IP. And the reason is simple. If you recall the slide that I show about the heterogeneity of application in the beginning, it just says that speech use cases are very different than vision use cases. And having a monolithic accelerator that deals with both is not very efficient. So the approach which is better is to fold the accelerator inside different IP and build them exactly the way you want them to be for that particular use cases. Now, this gives you two benefits. One that I talked about of the tuning the accelerator to your needs. The second one is it also saves the transmission of data back and forth from the system bus to the accelerator. And doing it this way, it doesn't have any contention. They're designed for the particular use case, and the data is local. And that helps quite a bit on the power as well. So to build efficient hardware for AR, there are a few things that we can do. Because the applications are very heterogeneous, it does require one to think about building heterogeneous accelerators, not just one monolithic accelerator. And they can be deeply embedded in where they need to be. To alleviate the problem of latency, one can have small batch side or very stream-friendly processing. And then, the data flow becomes very interesting when you talk about high resolution data. And there are lots of approaches of doing that using tiling and scheduling. And that's where the compiler and accelerator architecture together comes into picture. Now, from the system side, we still have this requirement I talked about, that we need to have 2 orders of magnitude improvement in efficiency. We need to figure out how do we deal with compute and storage issue, and also the shared bandwidth that I talked about. And the only way to solve that is through hardware software co-design. And I'll briefly touch upon that in the next few slides. So let's take an example of a neural net where you have, let's say for image classification, you have a neural net model. And then on the right side, you have an accelerator that can execute it. Now, if these two things are designed independent of each other, there is a loss of efficiency, right? Because you are not taking full advantage of each other. And the metrics that you can optimize for could be, you need high accuracy, you need low latency, and so on. The key insight here is that if you are able to optimize in an accelerator hardware, understanding what's going to be running on it, that will give you a lot more efficiency, but it doesn't need to flow only in one direction, right? The bottom arrow shows that once you have a particular way of running something in hardware very efficiently, you should be able to take that knowledge and apply that in designing a better model. So, if you look at the typical approaches of NAS or network architecture search, people search for either lower flops or a metric like that, but it doesn't preclude us from using a hardware-aware search scheme in your NAS as well, right? So this whole idea of co-design where we learn from the model characteristic in building the accelerator, and then we learn from what really works well in hardware and fold that back into the model is an approach that shows lots of benefits. And I'll have some data as well in the next few slides to show that. So to optimize and customize a neural network for a target hardware, neural architecture search has been widely studied. The typical conventional NAS methods leverage evolutionary algorithm or reinforcement learning, but they can be prohibitively expensive, as thousands of models are required to train to search for a single network. We instead focus on one-shot architecture search methods because of its superior search efficiency and accuracy. Specifically, we propose two frameworks focusing on searching the network layer hyperparameters and network topology. So the first framework we propose is attentive NAS. And this is some work which we recently submitted to CVPR and it's been accepted. So attentive NAS focuses on searching the network layer hyperparameters, including number of layers, kernel size, and number of channels, etc. And by improving the sampling method used in one-shot architecture search method, attentive NAS outperforms all existing methods on the ImageNet dataset. The second approach on NAS we have is called scale NAS, which focuses on searching the best network topology. So for example, the visual understanding tasks like pose estimation or semantic segmentation, scale variant representations are important because your different features could be of different scale. And that usually is a challenge in most models. So we search for the best network topology to enable multi-scale feature fusion. So this particular work has been really interesting. As you can see from the slides or the graphs on the right, that the quality of these models using this sort of NAS approaches is really great. Since I'm talking about NAS and hardware software co-design, this is the approach that we take. So you have a NAS which basically feeds off some sort of a profiler which gives you an indication of how the model does on the hardware. And this could be latency, this could be power, or this could be a combination of both. And that feedback basically goes to the NAS, and it looks at building different components of the NAS and ultimately profiling that to training of what that model does in terms of accuracy. And together, essentially, this loop continues until you get where you need to be. As an example on the right side, in many cases, you can have a good accuracy gain at the same latency, or you can keep the same accuracy, but you can have a significant latency saving. And we have been using this approach for a lot of models that we are building inside FRL. Now, I didn't talk about compiler support so far, right? Because this is also an important factor in multiple pathway architecture. So take an example of the audio visual understanding I talked about earlier, where you have multimodal inputs. You have audio stream coming in, you have video stream coming in, and they all look very different. So you have to have support for efficient network architecture, things like depth-wise, group convolutions, attention layer, and so on. Now, in terms of compilation, you can do a lot of different key innovations there. One is you minimize activation spilling. So activation spilling is a concept which means that if your activations that are generated in between the layers, they exceed the amount of activation memory that you have, then it has to go to DRAM. And sending data and fetching data back from DRAM is very expensive. So we need to do that to remove DRAM accesses. And then it will also improve your latency bottleneck by improving the memory access. So compiler is a key part of what we are building. And usually what we have seen is you just can't build an accelerator and then have a compiler as an afterthought. It has to be done together. In many cases, we have to start building the compiler framework much before the architecture is frozen in stone. So that brings me to my last slide. I talked about lots of different concepts. I talked about hardware software co-design, where we can improve system efficiency and so on. But there are a lot of future directions that are also interesting that I'm hoping the research community spend some time thinking about that. One is network hardware co-optimization. Is it possible to build an ML framework that can actually design the hardware and the network topology at the same time, right? So I talked about this whole multiple arrows approach of going back and forth. But imagine instead of doing that, if we can have an algorithm where both of them are sort of become the loss function where they get optimized together. And I've seen some work and they look promising, but a lot more work has to go there. In sensor and near sensor computing are especially important for these use cases because in many cases, you can capture images from your sensor, and if you look at them and nothing interesting is happening, then you have just wasted quite a bit of power because it wasn't really that important. What if we could build a model that can run in sensor or near sensor that detects if something interesting is happening, and if it's not, then you don't even send the data. So reducing the cost of data movement is really key. And I've seen some really interesting work happening in that particular domain as well. And the last one is lifelong online learning. We need these models that are running on the glasses to become very personalized. They need to understand each user and their particular nuances of how they use the devices. So having a capability to learn on device, it's really important. There's a lot of approaches of doing that, and we have been looking at some, but this is an area as well where we expect a lot more to come out of academia in the coming years. So with that, that brings to the end of my talk. I think we have done well in virtual reality. We have started to scratch the surface of what AR can bring. It's a long way to go, but we are very excited about the future. And I'm looking forward to working closer with lots of people in this community, both industrial partners and research labs. Thank you.
All right, thanks, Vikas, for that great presentation. We have a few questions, so let me go through them. So the first question is, can attentive NAS and scale NAS be fine-tuned to any hardware, or is it very specific to your own hardware?
No, they can be fine-tuned to any hardware. You have to understand that in the graph that I talked about here, there is a hardware profiler. Now, this profiler predicts what the hardware will do given a particular model. So as long as you put in the right understanding of the hardware that you have, the model that evolves using NAS can be tuned to that. So it's agnostic of the hardware. It has to be modeled rightly in your framework, though.
Mm-hmm. All right, makes sense. Can you elaborate on the on-device learning approach?
Yeah, so we have just started in this. So, and I know the other academic research that have done a lot of work on that. Again, there are approaches of federated learning, or there are approaches where you can have differential privacy-based learning, and there's a lot of lot more innovations happening in the last few years on that. This is an area that's in active research internally, so I can't talk a lot about it. But I mean, I know that even in academic research, there's a lot of innovation that's going on in there.
Right. I understand you can't talk about specifically what you guys are doing, but can you give some high-level view of what do you view as the eventual goal of on-device learning?
So the eventual goal of on-device learning to me is having specific things that a particular user does. So for example, when we talk about voice triggers, when we talk about different ways I want to communicate with my devices, there could be very specific things that we can give the capability for the users to train their models just with the specific nuances that they have, right? And that particular learning doesn't need to go and affect a global model that goes to all the users. So these are the use cases where I think on-device learning might be very interesting, where because of personalization context.
Right, right. That makes sense. Can you give some examples? This is another question. Can you give some examples of how the compiler can constrain the hardware specifically?
Yeah, so one of the thing with compiler is if you think on a meta level, right? What does a compiler do? It takes your graph and it figures out how to schedule different operations on the hardware. Now, if you look at NAS, where you're looking at network topology, and if you find that using NAS, as I've shown in this figure, and then you essentially say, okay, now that I have this model, let's figure out how do I compile that to the hardware. That's the current way of doing it. Everybody does it like that. But one potential approach is folding the compiler into the NAS itself, right? Because there is scheduling and tiling and all of these things that you can do with the hardware that has an implication of how you design the model. So initially, maybe you were worried about a large activation footprint because your data will spill, as I talked about earlier. But if you can tile your layers, that may alleviate the problem. So folding that compiler sort of inside the NAS flow gives you a lot more flexibility on what you optimize for, and it's sort of a joint optimization as well that we have been exploring.
Okay, so you envision that this is mostly static ahead of time compilers for AR/VR systems, or is it runtime scheduling?
No, so this is ahead of time, right? Because you know the graph exactly what you're looking at, so you can do ahead of time compiling.
Right, right, okay. All right, next question is from Kurt. So you know this is going to be a tough question. Relating to the attentive NAS, your archive paper principally focused on computer vision workload. Have you applied attentive NAS to speech recognition and NLP? If so or not, how much change do you expect will be required?
Right. So yeah, it is correct that we applied the SuperNet-based approach for computer vision task, where we figure out how to efficiently sample the Pareto of these models, and that gives us quite a bit of improvement. So yes, we are applying it to other use cases as well. We don't have any results to share, but hopefully we can publish something soon this year. Yeah, that's all I can say. But I mean, the early results that we see out of this work for speech and NLP model is definitely promising because in theory, this approach doesn't preclude any other use cases to be a part of it, right? Computer vision is something that is easier because there's a whole lot of data set and understanding of how to use it, and that's why we went after that. But we have been applying to speech and NLP models, absolutely.
Okay, that's great. Okay, so I guess I'll ask the last question, just a little bit more of a high level from a product perspective. Now, for AR glasses, power consumption is going to be very key because of thermal constraints and the battery considerations. So do you have a sense of at what point in terms of the energy per inference will be required in order to make AR glasses a reality?
Yeah, and then it becomes more of a product question of, because you can always enable a fewer things if your battery becomes important. Now that will make the product lose some of the features, and that may or may not be good. So from that perspective, there is always that knob. Now we don't want to go that way because we want to have more and more features as much as we can to make these glasses really interesting for the users to use them. And that's why the work that we have been doing is to make sure that where can we get more and more efficiency out of the system. But in the short term, if it still doesn't fly, because a lot of the work is in flight in terms of model architecture, in terms of building the right hardware, then we have to really see what features does need to exist on these glasses. So this is the first inning of AR, if I may. This is going to take a while. It's going to take a community to build where we need to be. If you look at smartphone, like the smartphone from 2005 looks very different than the smartphone that we have in our palm right now, and it took a long amount of time to get to where we are right now with all of the applications and how seamlessly things run. And so you'll see that evolution with these devices as well. But we need to start investing in making sure that there is a path to get there.
Right. So much more to come.
Absolutely.
All right. Thank you, Vikas. That was a great presentation.